Hey everybody, welcome back. This is lecture number 21, I think. And what I do know is that today we're going to cover ensembles, machine learning ensembles. Before we get to the fun part, let's take a look at the logistics situation. Yeah. So by the time you see this lecture, it probably won't be relevant to you, but at 11 a.m. Wednesday, December 2nd, we are going to have Eugene Izhikevich as our guest lecturer. He is a computational neuroscientist turned entrepreneur who runs, he's done a lot of cool things over his career, starting with a very neat, very simple model which captures amazing dynamics that you can use to understand the way neurons work on a cell-by-cell basis, and use that in turn to understand how networks of neurons work. It's computational neuroscience kind of model, less concerned with machine learning and trying to solve problems, and more with trying to understand the mechanisms of biological learning. So that's a pretty cool thing that Eugene has done. And then he took that and used it as a lever to try to create his own company, which uses an understanding of how the brain learns to solve real-world problems in autonomous robot operation. And they run a very large number of robots for millions of hours of operation in real industrial and public settings, around people. So it's pretty cool stuff, and he has an interesting company and an interesting background, and so I think we're going to have a lot of fun talking with him. So please come out. Now, the rest of the stuff, homework number 6 is out. It's due on Sunday. I gave in a few extra days, so Sunday at turning midnight into Monday. Please try to get us at that point. But if you're struggling right now, if there are just too many things going on with your whole school career, please come talk to us, okay? I am aware of the several people who are struggling right now. And if you are, don't try to just hold it all in and end up with a problem in several different ways, okay? Please come talk to us if you need an extra day to sort something like a homework out. These are possibilities, okay? There are firm deadlines in the end, but what's much more important to me is that you learn something and that you don't go crazy trying to learn something, okay? So in regards to both the homework and to a much lesser extent the final project, we can have some small flexibility, okay? So let's see. Right, so let's get on with the show. All right. So what are ensembles? Ensembles of machine learning systems are when we put together multiple different classifiers or regressors or whatever into a system that combines all their answers and produces a unified output. The basis of all this is the idea of wisdom of the crowds. Maybe you're familiar with the concept, but I'll recap it real fast. So it turns out that if you have a bunch of people who are bad at something, and they're all bad at it separately, independently, and then you put together their thoughts on the matter as a group, they can do better as a group if you take the average of their thoughts than they would as individuals. So a concrete example is usually the giant jar full of marbles. You look at it at the fair and you guess, oh, it's got 1,122 marbles. And the next person comes along and makes a separate independent guess. Oh, it's 24,009, right? So everybody's wrong. everybody's wrong in different ways. Everybody's making their own mistakes. But when you take all of their answers together and average them, you will get an answer that is remarkably close to the right one. And this is what we mean by wisdom of the crowds. And the key part is the independent mistakes. Okay? So to combine the beliefs of a crowd, whether it be machine learning systems or people, one common way we use to do that is voting. Okay, so voting takes place in a variety of different ways. You can require a unanimous vote, or a majority vote, or a plurality. Now, if you're not a politics geek, you might be forgiven for not knowing that there is something called a plurality. But what a plurality is it's just you have a case where there is one winner in the sense of this one got the most votes, but that winner has not captured at least half of the vote. Okay? So when we do machine learning stuff, we will sometimes be okay with a plurality in voting, but usually when we are properly talking about voting, we're talking about a majority vote, where we would like to get half of the ensemble to actually all line up behind a single candidate. Okay? Now, as we know, many times voting is controversial, so it is always important to count every single vote. Wow, my impression of the count scared my cat. All right, so a majority vote classifier. So how does this whole thing work? We have a voting system. We combine a bunch of different classifiers. So in this case, we're going to say that each classifier is labeled as H, H1, H2, so on and so forth, up to the N classifiers that we have in this system. And each one of them is trained with the same data and tested with the same data. But each one is learning on its own from that data and will be making independent mistakes. Each one outputs its own predictions about whatever the data is, and we take a majority vote system. Okay, something that's important to note is what happens when you have the mode of a distribution. Well, the mode of a distribution is just the most common element. Thanks, Magic. You're literally stepping on my keyboard and activating everything. Go away. Go away. And now he's going to drink my water glass. All right. So the mode of a distribution is the most common element. So if you want to know who took the majority vote, then you can use the mode. All right, so that's down there. That the output of the final stage is just the mode of all the independent predictions. All right. So what's up with the majority vote? Well, the thing that we can do with the majority vote is that we can talk about it as a probability of getting things wrong. Okay? So we can look at it as a binary classification task. And when we do that, when we're looking at, so the binary classification task is a simple toy version of what you can do with more complicated systems. Okay, so we're just going to learn about the binary version so that we can all talk about it in the simple thing. I'm sorry, I'm super distracted because Magic is being some of the worst that he's ever been. He's already bumped my camera. All right. You're going to meow for them at least? Thank you. All right. So let me get my mind back on the matter at hand. So we're going to assume n independent classifiers, right? So they each make their own mistakes without reference to the others. So that is their errors are going to be uncorrelated. Go away. All right, so their errors are going to be uncorrelated. And a critical thing that's going to help us out if we assume that the error rate is better than random chance. Okay? What is random chance for a binary classification task? It is, of course, 1/2. Binary is the coin flip. Assumedly, it's 50-50 coin. It's a fair coin. So in that case, we will have random chances 1/2, and we need to do better than that with our individual classifiers. Okay, so if we cast the problem this way, and we want to know, with a majority vote, what is the probability that we make the wrong answer with the entire ensemble? Okay, if the whole ensemble guesses wrong, how is that going to happen? Well, for a majority system, we need to have more than half of the classifiers all saying the same wrong thing, right? They all have to vote for the same wrong candidate. We won't bring politics into this part of the discussion, okay? So if more than half of people vote for the same wrong candidate, then the whole system produces the wrong answer, right? So how do we measure that probabilistically? Well, it turns out that that's merely just the binomial distribution, right? A binary choice. What is the probability that the binary choice turns up a particular way? Okay, for a majority voting ensemble to say the wrong thing, you need more than half, okay? So that's the critical element here. This number k is going to be n over 2, right? It's going to be greater than n over 2. K has got to be at least half of the ensemble voted for this bad thing. Okay? And of course is our number of samples. And so that just gives us the probability of making the wrong pick as the binomial distribution, n choose k, times the probability of making a mistake. That's the error. So that's epsilon to the kth power times 1 minus epsilon to the n minus kth power, right? So let's take a concrete example. Let's say we have an ensemble of 11 voters. Now, why is it 11? Why is it an odd number? Bueller, anyone? Yes, front row, green hat. Yes. When you have an odd number of voters, then you're guaranteed a result. Okay? At least if you are allowing a plurality situation. You're never going to have a deadlock. With an even number of voters, you can have a deadlock, i.e. juries where there's 12, which just built for deadlock, right? Okay. So, all right, so we have 11 voters in this setup. So we need to get at least half of them to vote the wrong way. So half of 11 is 5.5. We don't have half a voter, so we round it up to 6 because we need at least half. So we do the binomial thing. We sum up from 6 to 11. So we do 11 choose 6, right? And we put in the numbers of whatever our error rate is. So in this case, let's say our individual members of the ensemble have an error rate of 1/4. Okay? Comes out that the probability of the entire ensemble making a mistake is around 3%. Each individual of the ensemble, each element, each classifier, is got a probability of being wrong of 1/4. But it is much, much less than that, the probability that the whole ensemble makes a mistake. Pretty cool, huh? All right, so let's take a look at this over many base error rates, right? So as we vary the epsilon here, so this base error is epsilon, okay? As we vary the base error back and forth with this system, and we plot that function there in blue, we see a lovely sigmoid. What does that mean? Well, if you look, here's our magic be better than chance level. So we only care about the stuff on this side of it. And it turns out that if you plot the error of the base here, we get a diagonal line, of course, because base error versus error rate. Each classifier has got this amount of error. We see that the ensemble is always less, right? It's always going to be less. And even better, it kind of shoots towards 0 very, very quickly. So we can see that the power of an ensemble and voting far exceeds the level of accuracy of any individual classifier. All right. So there's another way to do voting. What we talked about just a second ago was hard voting, where we just have a preference and we put it out there. You can also put out a preference with a predicted confidence in it, right? So the predicted probability that a given input should produce a given output, right? So if you have, for instance, a situation like this, you can weight the outputs according to confidence. So classifier 1 says option A, and I'm just a little confident. And classifier 2 says option B, but I'm very confident, right? I have strong probability. You might weight those two things differently when combining those votes, okay? And that's a soft voting system. So we take the probabilities of belief in each labeling. And this is only applicable for well-calibrated classifiers. What does well-calibrated mean, I hear you ask? Because I've been confused on that, you say, since that was in the Caruana paper. Well, yes. The idea of a calibrated classifier is that the values that it outputs are in fact usable as probabilities. Okay, so obviously it has to have certain criteria like, you know, the outputs of all the possible classes sum to 1. Okay, since probabilities have to be, you know, summing to 1. There's also an element to it that you need to be able to calibrate it to produce not just the right kinds of numbers, but the right numbers overall. So there's a way in which you can actually calibrate to a training set. So that's the stuff that is in Caruana is called isotonic regression. I'm not going to get after that in this class. That's why I kind of passed it by during the project write-up stuff. But the vague idea is that you are trying to literally figure out how to transform an output into a probability. And you're doing that with another learning system on top of the first one. Okay? So that's about as much as I want to say about that. But you can either use a classifier like a logistic regression, which is inherently calibrated, or a softmax neural network, or you can take an uncalibrated classifier and calibrate it with a second learning system on top. All right. So let's go through an example of soft voting so you understand how it works. So the output of the soft voting system is going to be taking an argmax, right? So we find the element j, and the j being which class we're voting for, okay? And we sum up for all classes the probability that, so let me make sure I do this right, probability of classifier I is going to vote for element j. Okay, so we're gonna, this is the classifier. It's all, in other words, it's that, right? And this is the class, the thing we are voting for. Okay, the vote getter. Okay, So in this example, we have 3 classifiers, 1, 2, 3. I'm getting flashbacks to reading books to my toddler. 1, 2, 3. All right. So here are the 3 classifiers, and these are their outputs. So we are voting for class number 1 with that probability, and class number 2 with the second column there. Okay, so here's what we have to do. We have to find out the probability that the whole system of classifiers should vote for 0 or 1. So we go ahead and fill out that for each one of them. So we get 0.9 is our vote from H1 for class 0, right? And 0.8 is our vote for H2, and 0.4 is our vote for from H3. And we have these weights here, which are something which in this case have just been assigned. Okay? There's some sort of reweighting system that we have in mind for this setup. Okay, those same weights, right? 0.2, 0.2, 0.6 here, they all apply across all of the votes, right? So now we're going to tally up our votes for the class 1, and we get that column right there and put it in. All right? So what maximizes? Well, clearly it's class 0. All right. So let's stop with that for a second and start a new topic. The Bootstrap is a way to do things in statistics. Okay. What does the word the Bootstrap mean, right? Coming from this weird idea of to literally pick oneself up by your own bootstraps, by the straps on the back of your shoe that you help you get it on, right? Why cannot a man lift himself by pulling up on his own bootstraps? Well, the idea was to teach people, of course, that for every action there needs to be an equal and opposite reaction, right? And clearly this kind of archaic term was just ripe for reappropriating, and so it happened several times. We get the meaning of to better oneself by rigorous, unaided, impossible effort. To pull oneself up by one's own bootstraps is an English phrase that for people of my generation and older definitely has a commonality. But in the modern era, you may understand the bootstrap as, especially since you're kind of computer savvy, as the bootstrap loader, the first element of a computer turning on. Okay? But in this world, in statistics in general, that is not what we mean at all. What we mean is sampling with replacement. So the bootstrap is just when we take a set of samples, a training set, right? And we draw from that set of samples, we put our hand in the bag and we pull out whatever. We pull out one of these red dots. And we go, okay, so my new sample has a red dot in it. But we don't put the red dot there and leave it. We record the red dot as having happened, and we put it back in the bag so that we can draw all over again. Okay. Of course, my system is deciding to fail here. Okay. Let me try to restart my keynote presentation. There we go. All right. So when we finish drawing and recording what we've drawn out of the bag, then we are going to put it right back in. And then we draw again. And again and again and again. And because we keep putting back after we record, we are going to inevitably draw the same thing more than once, right? So we're going to end up in the end with a bunch of these little red dots and just one of the green dots. Okay? And for, the reasons of random chance, we never see any of the blue dots or the crosshatch dots. Right, that is the bootstrap. It is merely a funny word for sampling with replacement. So what happens when we do bootstrap sampling? Well, as I said, inevitably, some things get chosen multiple times. Some things never get chosen, right? What's the probability that, that cross-hatched blue one never gets chosen? Well, you can write down the probability as, at each moment that you'd make a draw, you have a 1 over n chance of drawing. So not choosing something is 1 minus 1 over n. And not choosing something after n samples, okay, would be 1 minus 1 over n to the nth power. So this, as n approaches infinity, this approaches the number 0.368, which is 1 over e. So that means that as we approach large and larger numbers of samples and draws, that what we get is that on average, 36% chance per sample that it never gets chosen. Okay, we can look at the flip side of that, right? So the flip side is 1 minus the quantity we just came up with. That's the probability that a given sample will be chosen. And that approaches 0.632. Okay, so this shows you that when you do repeated sampling of the same data, right? So we have a big data set. We're going to pull it up and we're going to resample it. When we do that, we expect that anytime we do that, that we only choose about 60-ish% of the possible data points, and that 30+% of them are going to end up not chosen at all in a given data resampling. Okay, so I'm going to stop here for a part A, give you a chance to rest and absorb that before we head on to apply it to some machine learning stuff. All right, bye for now.